So this is about computational thinking, and we have discussed this part in the last class as well. Your syllabus says that you need to discuss the elements of computational thinking, and you need to discuss what is meant by computational thinking. So the first thing is thinking abstractly. So first of all, we will be discussing the nature of abstraction, the need of abstraction, the difference between abstraction and reality, and how we can devise a model for variety of situations. Do you know what is an abstraction?
Abstraction is removing the unnecessary bits and you're focusing on the details that are important. One example can be is like if you're organizing something into different bits, it'll be easy for us to tell which one is needed and which one is not.
Yes, thank you so much for your answer. We discussed this in the last class as well, and here is basically the summary of what we did. Computational thinking is about a set of problem-solving methods which expresses your problems and solution into a way that a computer can execute them. So computer professionals have developed this to solve real world problems and turning them into computer sciences. Like there are some techniques known as computational thinking. Computational thinking like does not require a computer, but it can be implemented on one because you are thinking on the set of problems that you have to solve it. So computational thinking is like used to change a problem into something that can be well understood and formally documented. So there are certain steps that we need to work on. Like the first thing is for abstraction of a problem, the steps involved. Well, first of all, you need to understand the problem. Understanding means how do we know that we can understand a problem sufficiently? This means that this does not mean that we understand the solution, but it is what we are trying to do. How can we formulate the problem? In this stage, we need to produce a concise representation of the problem. So it's like normally it will involve abstraction and some form of notations as well. Then we need to design the algorithm. So it's like once a clear representation of the problem is obtained, we can work on designing that. And then we need to implement the algorithm and run the code and solve the original problem. So the first point in the computational thinking is that you need to understand the problem. The second part is that you need to formulate the problem. The third point is that you need to design an algorithm, implement the algorithm, and then run the code and execute it to check that if it is working properly or not. Similarly, in computational thinking, we are actually checking how the computer helps us to think. So it's like you can get the technology to do all the hard work for us. Or maybe the problems in the past involved just too much work or time can now be tackled extremely quickly. And we have to do that by first formulating them into a way that they can be processed by a computer. And for this reason, we use these methods where we can understand them, formulate them, design them, implement them, and execute them. So some examples of computational thinking are right here. Like not many years ago, anyone who was engaged in some form of creative writing would have to use a pen or maybe a typewriter. The writer of a factual book would need to make copious notes and keep them organized so that a product can be made. But such writing necessarily involves numerous revisions, and you need to cross out many things like throwing paper away. And it basically takes a lot of your time and takes a lot of your paper. So this is solved like these days when you have those digital tablets and the digital drawing tools where instead of throwing away the papers and instead of making the models again and again if they get wrong, you can do that easily. But how the computational thinking helps us is that first of all you look at the problem, you assess that how difficult it is, then you basically use recursion. I explained you recursion in the last class as well, that if you are applying something repeatedly with some set of value. So this is recursion, like doing that again and again. Reformulate a problem into something familiar that we know how to solve, and or model a problem so that we can create a problem that can run onto your computer system, or look at the proposed solutions and assess it for elegance. You can also check for built-in processes to our solutions that limit the danger, damage, and recover from our errors, and scale our solution to cope up with even the bigger or the smaller problems. So it's like when we look at solving the problem with the help of computational thinking, we have to decide what part of problem has to be solved first. This is going to link back to the age that computer works with an algorithm. So you need to format that and do that. So in the part of computational thinking, the first area is that you need to think abstractly. Do you know what is this? Like, what is the need of abstraction, or what is the nature? Do you have any idea on this?
Yeah, the nature of abstraction is the process of hiding non-essential detail or like remove any unnecessary bits, and you're focusing on the bits that you need. For example, you can like organize the bits where you want to organize things,
Mm-hmm.
like so that it will be easy for us to tell which one is needed and which one is not.
Okay. Thinking abstractly means, like, first of all, abstraction is the representation of reality. So this is one of the process of hiding non-essential details and leaving only the key elements of the problem. That means that you are focusing on only it is required. So this process can require us to recognize what is important in a problem, and then it can be formulated in a way that we can pass it to the algorithm. So if I'm talking about the nature of the abstraction, which is a part of your syllabus right here, the nature of abstraction. So it is more likely a representation of reality, and you are focusing on only what is required to you, and you are just leaving away or eliminating the key elements of your problem. This is the process of hiding non-essential details, like leaving away the key elements of your problem. So this process recognize us to recognize what is important in a problem, like what is important and how you can formulate that and how you can pass it to this algorithm. So then the algorithm can be used for the coding solution. So for example, of abstraction, some examples could include like variables, objects, layers, data models, data structures, ER diagrams. So this is basically the nature, right? Like the four things listed here. Can you give me some pointers for this? Like, what is the nature of abstraction?
Okay, so the nature of abstraction is to basically filter out the unnecessary details and focus on key points.
Okay, so one pointer that I can write here, just a moment. Yes, okay. One pointer I can write here regarding the nature is that abstraction is the process of removing unwanted or unnecessary details and focusing on only what is required, or you can say that it focuses on only the essential characteristics of a problem or system. This is basically the first point. Anything else you can say for this is that the nature of abstraction is that abstraction simplifies complex realities into a model which is easier to understand for us and easier to work as well. For example, a map. This is an a map is an abstraction of a real world where it shows you the landmarks but omits irrelevant details like individual trees, buildings, or any unnecessary part, right? Like, or you can say cloud as well, which is not necessary for you. So, in terms of the nature, is like you are focusing on only what is required. Do you have any problem in this?
No.
Then, if I move on to the need for abstraction, can you give me any point?
Um, the
What is
need
the
of
need for this?
abstraction. Okay. It is to mainly make it easy for us to tell which one is important, which one is not, which will basically make the program easier to solve and simplify complexity, allowing us to focus on essential features.
Okay. So, one thing I can say that sometimes, sometimes working with real world systems can be too complex to understand and work with. The need for abstraction is that if you implement or use abstraction, it will allow you to simplify your problem as it will become more manageable, and then you will be able to understand, work in teams, or manage it efficiently, right? That's the first point. The second point is that with the help of abstraction, you can design data models that can be implemented into a program and which are easier to understand as well. And when I talk about these data models, as I explained with you right here, so example of these data models or abstraction could contain like we have these examples. See, we have this variables, objects, layers, data models, data structures, ER. So that means that you can convert them into this data model and you can work with it. Another need is that now you can focus more on the logic of a solution rather than any irrelevant details. And without abstraction, without abstraction, solution would be overcomplicated, hard to maintain, as you will be having a lot of information at one place to manage and complete. Are you getting my point?
Yeah.
This is for the need of abstraction. Then when I move on to the third point, which is basically the difference between abstraction and reality. Now, do you have any idea regarding this abstraction and reality?
Okay, so abstraction removes details to focus on essentials, and reality contains all the details, even if they are irrelevant.
Okay. So the difference between abstraction and reality is that if I just summarize this, when it comes to an abstraction, it's like a simplified model where you show only the relevant information. Whereas if we talk about reality, it's like it contains all details, many of which are even unnecessary for solving a problem. This is reality, right? So when you want to work with the things down, you need to skim the things up, like only things that are important for you, and that is abstraction. But in reality, there can be certainly more number of things which are important, which are not important. So let's take an example. For example, when it comes to reality, we can say it might contain all details, many uh, of which are unnecessary. But one example can be a self-driving car that needs to process every camera pixel. This is reality. But when we go on to abstraction, it's about the software may just consider the detected lane lines, traffic lights, or vehicle. This is one of the example. Can you give me more example for this?
Mm. Reality will be like a scanner will basically need to scan every item, yeah, that is bought from the shop, and the abstraction is that for example, for abstraction we could say if any items have coupons or not.
Okay.
Is that fine?
Yes, but let me show you some more example. Can you see the other example which I have done here?
Yeah,
Does this make sense?
yeah,
See, does this make sense?
yeah,
Or you can also say that when it comes to reality, it's like a person's entire life, personality, habits, emotions. And when you do the abstraction, it's it's only the name, profile picture, post, likes of the person, right?
yeah.
So that's how we are differentiating them. Then with the fourth part, which is devising an abstract model for a variety of situations. What do you say about this?
Oh yeah, sorry, I was muted. Oh yeah, like setting an organization.
Mhm. For example, if I give you a school timetable, what is going to be reality and what is going to be abstraction for a school timetable?
Reality will be all the subjects, uh, teachers' classroom,
Yes. And
and
abstraction will be
days,
representing,
each subject.
this is one example. Or let's say traffic
Teacher,
light system. When it comes to reality, it's like wires, bulbs, weather, wear and tear. But what is abstraction? The abstraction is when you have only three states such as red, yellow, green. Well, you know what is an object? An object is a this is a data type. We will see this later, but it's like when you are requesting it to turn that into a data model. So data abstraction can be used in data structures as well without being concerned about how it is being implemented. So programmers might well use a subprogram to manage a stack, queue, or linked list without needing to know how these data structures are being implemented. So large projects programmed by teams often use routines developed by others without needing to know how they work and just what they do. Generalization is also a part of abstraction. It's like when you group them all together, where you have items with similar features that are relevant to the problem as well. So grouping is one of the examples. Like ignoring any part which is irrelevant. A common approach may already exist or can be created maybe from existing solutions or similar problems. You can work with layers by organizing problems into separate functions and components that act with each other. You can work with data models that organize elements of data and how they relate to one another. You can work with ER diagrams that shows you a graphical model to represent the relationship. So all high coding is an abstraction because one high level command may can also give several machine codes to complete. Here is an example. The example says that when you are designing a game where your characters move around a virtual landscape, the programmer will remove unnecessary details when planning the layout of the landscape. The character will be replaced by a simplified version, and objects such as plants and trees can be represented by a block of colors or simple shapes. So none of the detail is significant to the layout of the game. So therefore it is removed so that the programmer can focus on the characters and movement and an environment. You know what is generalization? It's like solving new problems based on previous problems which we have an existing solution. We can also know the need for abstraction as well, and I discussed that. So abstraction basically enables the programmer to focus on important aspects of a problem rather than getting bogged down. So it's like it enables team of programmers to work on different aspects of problem and at the same time, it also enables programmers to use pre-built and built-in functions without considering how they work. So layering is an example of an abstraction. So it's like how one layer is implemented on one and another. It's like programmers that are developing one layers of whole system that is necessary that they know that what input requirement and what are the next layers. Regarding the differences between abstraction and reality, is like abstraction is just simplification of reality. You are just simplifying that. There could be entities in real world that are represented by different data structures, but the real world data is the value stored in those containers. So in object oriented programming, the objects are abstractions of real world and entities. We will discuss this in detail regarding objects and classes. And how you can devise an abstract model to a situation is like a computer program is efficiently an abstract model of real world situations. But when you are developing such models, you need to consider, like, first of all, can you solve the problem by using a computer program? If yes, then you need to ask yourself that what are the key features of the problem? How are they going to be used? Who will be using them? What are the skills? What are the features? So when you consider all these factors, it's like then you turn out into suggesting a model, right? Like, for example, it says that when you are fitting a new room, such as kitchen, interior design program that are often used, the basic program will start with some basic objects that can be resized or modified, right? Like, you can work with basic room shapes, standard graphics for doors, windows, blocks, but the details of this object is not required when you are designing the layout. For instance, the model does not need to show how the hinges on the cupboards will operate, and using the simplified model, it could be possible to construct a working layout to examine how things are working. Do you know the concept of decomposition? It's like you break down your problems into even small parts so
It's
that you can
it's to
solve
break
the
down
problem.
big
Yeah, yeah,
problems into smaller problems.
yeah. You can do that recursively. That means that you can run it again and again. This will also come, or this will also come here. This is one of the area of computational thinking like this. But a drawback of that, it assumes that the whole solution to a problem is known in advance. So this hierarchical approach is also less useful with many modern applications as well. Decomposition does not have to be hierarchical. It can take into account parallel processes as well, alternate processes as well if needed.